Hi, thanks for stopping by. In this video, we are going to present UNEM, Unrolled Generalized EM for Transductive Functional Learning. Functional learning addresses the challenge of making accurate prediction from very limited label data. The goal is to classify query examples using only few label examples per class. These are known as support sets. In modern functional learning pipelines, we usually start by extracting the feature and use a pre-trained model like a ResNet, Vision Transformer, or multimodal models such as CLIP. From here, we have two main strategies: the inductive approach that classify each query independently using the support sets, or the transductive approach, which we focus on. This one considers a batch of query samples jointly. The joint reasoning helps mitigate the distribution shift between the training and evaluation data, which is a common challenge in functional tasks. However, state-of-the-art algorithms introduce key hyperparameters that significantly influence the prediction performance. Usually, these hyperparameters are selected through research and a validation set, which might be an expensive manual process that doesn't adapt well to new tasks and domains. So we propose UNEM, which is an unrolled version of the generalized EM algorithm, which allows us to learn the optimal hyperparameters directly from the validation set, removing the need for the research. So the goal of our problem is to identify the classes of unlabeled samples in the query set with the supervision constraint from the support set. We do so by optimizing objective function over the set of soft assignment vector UN and feature distribution parameters theta k for all the classes. We derive a minimization problem that contains a data fitting term, a partition complexity term, and an entropic barrier. This problem can be solved with an iterative block coordinate descendant algorithm, which alternates three steps: the distribution parameters updates, the class assignment optimization, and the partition complexity updates for L iterations. Please note that in this generalized expectation maximization algorithm, it contains critical hyperparameters. So now, what's the unrolling paradigm? Well, the core idea of unrolling is to convert a fixed number of iterations of the EM algorithm into the layers of a neural network, where each layer represents one EM step. And by applying a loss function at the end on the soft assignment vectors, we can train the hyperparameters using a backpropagation. Then we use softbox activation functions on the hyperparameters to ensure they stay positive. And also we can allow different hyperparameters to be learned across the layers, giving the model more expressive power. So this approach turns a classical rigid algorithm into a flexible and learnable model that adapts across tasks. In our experiment, we trained UNEM with 10 unrolled layers. We used a cross entropy loss at the end of the layers, and we used the Adam optimizer. We selected the query set size equal to 75, which means 75 samples are predicted jointly. We evaluated UNEM in two settings: vision only, assuming Gaussian prior distribution, and multimodal setting, where we use CLIP zero-shot probability vectors as input representation, and assume Dirichlet prior data distribution. In both cases, UNEM outperformed existing methods in the main benchmarks, achieving higher accuracy. So, in conclusion, UNEM transformed the classical EM algorithm into a trainable neural network. It automatically learns key hyperparameters removing the critical need for costly research in transactive feature learning. And it offers a flexible solution for transactive feature learning, outperforming the state-of-art algorithms in both vision and vision text settings.